make note of our domain and range. That's important. I want to start, see, this is our domain and this is our range for the regular sine function. It didn't change when we did a horizontal shift, okay? Now, remember this domain and this range. I want to start our discussion by asking you guys, what is a function? How do you know if a line is a function? Tell your neighbors, go. Now, the cheapest answer that I heard, but true, is if the line passes the vertical line test, it is a function. What the heck does that mean? That means if you draw a vertical line anywhere on this graph, and as long as it doesn't cross the curve twice, then you have a function. A more precise academic explanation would be every x value has exactly one y value attached to it. So that means if I were to draw a table, there would be no repeats in the x's. It's like, for example, pi over 2 right here. That only equals 1. Pi over 2 equals nothing else. You can't say it equals 2. You can't say it equals 1/2. It equals nothing else. It only equals 1. But it is kind of tricky because if I take pi over 2 and if I add the period to it, then that would be, let's see, what would that be? So the period is 2 pi, so that would be 4 pi over 2. So I would get 5 pi over 2, 5 pi over 2. If I went to 5 pi over 2, which is not on my graph because I stopped right here at 2 pi, but if I went farther, what would the max be? What would the point be right there? It would be 1 again. Okay, so is it still going to be a function if I have two y values that are the same? Yes. You're allowed to have a repeated y value, not allowed to have a repeated x value. This is a function, it is a function, it is a function, but it is not a one-to-one function as it stands right now. And you guys are going, what the heck's a one-to-one function? Well, let's see. I'm going to talk about sine and arc sine. These are inverse functions. You guys remember, what do you think of when you think of inverse functions?
Negative, right?
You think negative? Like, what's the inverse of multiply? Divide. Do you guys know what the inverse of add is? Subtract. Do you guys know what the inverse of square root of x is? What's the inverse of square root? Squared. Like, those are inverses of each other. So if I drew this line, this is a square root function. It does have an inverse. And I know that because I can draw the y equals x line, and I can reflect this curve to look like that. So it reflects over the y equals x line. If I were to draw a table, let's see, if I were to draw a table of my square root of function, I would only have one x for every y value. Like if I plugged in 4, what would I get? 2. If I plugged in 9, what would I get? 3. And only that. Like, I would not be able to plug in 9 and get anything else. Okay, so our inverse function would take the x's and the y's and it would switch them. That's what an inverse function does. Now, some of you guys might be thinking, well, then the inverse function for the square root function would be x squared, right? Mm-hmm. And so if I put a 2 over here, then I should have a 4 right here. And if I put a 3 over here, then I should have a 9 right there. So the x's and the y's switched. You guys see that? So the square root of x does have an inverse. But does the x squared always have an inverse? Oh, x squared. Does x squared have an inverse? See, check it out. Check it out. Look at this. If I put x squared right here, we have a parabola.
Yes.
All right, now that's a function, but does x squared have an inverse?
Y squared.
Yeah? No? You guys not sure? Yeah, y squared? Okay, let's talk about that. There you go. Here's my x squared. Now if I switch this x and this y, I should get the inverse function. Is that a function?
No.
No, it is not. Why is this not a function? Because if I draw a vertical line here at 5, I will hit the curve twice. That 5 would have 2 answers. So how can I say that x squared has an inverse function? This is what you can do. You can limit its domain. Okay, check it out. I could say x has to be greater than 0. Or I could say greater than or equal to, let's see, greater than or equal to 0. Boom. Now would this have an inverse?
Yeah.
Yes. Now if I switch the x and the y here, I need to say the y. I had to switch this y also. And there you have it. There's my inverse function of x squared. So if we restrict the domain and the range, we would be able to have an inverse function. So here, let's check out our friend sine. Okay, here's my sine graph. Would this have an inverse function? Let's see. If I just switch the x and the y, is that an inverse function? This is definitely the inverse, but is it a function? No, because if I drew a vertical line, even just look at the y-axis right here, it is hitting this curve multiple times, not only once, which is what our definition of a function is. So how can we make sine have an inverse function? Here's my sine graph again. The question is, or the task is to see where this function starts repeating the y values. Now if I start right here at 0 and I start going, my y values haven't been repeated yet. When do the y values start getting repeated? Right here. Right here. Hey, we're repeating the y values. All these y values get repeated right here. So could I limit my domain to be from here to here and just have this as my curve? And couldn't I have an inverse of that? Technically, yes. But can I make this interval wider? Can I have a bigger one that does not have any repeating y values? All right, so from where to where? Where do you want to go? Where do you want to go? You want to go from 0 to what? And you want to go from negative pi over 2 to positive pi over 2? You are right. How come we don't go from positive pi over 2 to this one? Wouldn't these y values not repeat either? Yeah, you are right. I can actually pick go as long as I go from the extrema to the extrema. We have no repeating y values, but yes, you know what? We end up using negative pi over 2 to positive pi over 2. And we limit our domain that way. So check it out. I put my 2 boundaries right there. If I zoom in, check that out. If this was all my sine function that I saw, I can definitely have an inverse function for that. As long as I go from negative pi over 2 to positive pi over 2, then I can have an inverse function of that. So here, check this out. If I did that, this is what you would get. Oops. Gotta get rid of these guys. There you have it. This is sine inverse. It's the same as saying arc sine. Here's your sine inverse. And if I put this graph back on there, you guys can see if I switch this x and this y again, they line up. Let's make this brighter. So here is arc sine, and here is the true inverse of sine, but it continues. So it continues on, but we just want this part right here. So that is arc sine. Now it's really, really, really important for us to note what the domain is and what the range is for arc sine. Now just look at this. Look at this picture I have right here. What is my domain of arc sine? -1 to +1. And isn't that the range of sine? If I had sine x, what's my range? Remember, it goes like this. It goes like this. It goes -1 to +1 for my range. But now the domain for my arc sine is the same. What about the range for arc sine? What would that be? -π/2 to +π/2. And those are also inclusive, so we include those in there. And that was the domain that we gave to our sine function so that we can have an inverse, -π/2 to +π/2. Using this information, now this is really, really important information right here. This is all about arc sine of x, or you can say sine inverse of x, because these are both the same functions. You have to know the domain and the range in order to solve its problems.